Now everybody received the typed note. It's a little bit better. Okay. Now, but anyhow, as I took it, two problems. I took it from various books, collecting them together, so the notation might not be uniform. Okay, and I leave that to you as an exercise, because this is also because, you know, reading blah 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 blah, you don't understand anything. So I leave you as an exercise to understand why this guy changed notation here and so on. This is important. Okay, so I do on purpose. Now, most probably I imagine that many of you have seen already special relativity, so we don't need to, I don't need to give you many more details. There will be 3 more lectures on special relativity, this one and the other 2, maybe 3. And I will have already prepared the notes, so I will send. Now, what I want to do a little bit in order to help you, we will work out one of the homework together, okay, today. It does not mean that you don't have, of these, I will work out, so you better take notes, because I will not send the note. And this is the homework that was on page 7 of the lecture number 2 that had titled Relativistic Dynamics number 1. And if you go to page 7, there is an homework. But let me, before doing that, just please. No, okay. The point is the following. You see, if you define the momentum, and you know, when I use the Greek index mu, it means I have 4 components. When I use the I index I have only the space component. This is the time, this is the space component. Now, what happened is we did the following at the beginning. M dx dt, and that we see did not work. There is no conservation. But there is also a more important problem that is the following. You see here, when you do a Lorentz transformation, you change both the numerator and the denominator. Okay? So this object has not well defined the transformation property. If instead you use dxi, and you divide not by this time, but by proper time, this proper time is an invariant, is a relativistic invariant, it does not change. Then this pi transforms as dxa, that means as a vector. Okay, so the physical reason, if you want, is if you use these, besides not having the right Lorentz strange transformation property under Lorentz, because both the numerator and denominator change, this one is not conserved. Okay, and why we cannot accept quantities that are not conserved? Because you have seen the Noether theorem in mechanics, most probably. You know, every conservation law is associated to a symmetry, and the conservation of momentum is related to the translation symmetry, and we know that the universe is translation invariant, so this must be conserved. So I prefer to have that approach more physical, saying, but another approach is the following, that this object, we want that it becomes a 4 vector. That means it transforms as dxi. And so below we put the proper time. And you know, the proper time, it has also intuitively a physical meaning. After all, the velocity of a particle is the particle itself that defines its own velocity. So you have to be on the frame of the particle, okay? And somehow, but let's say, first, so the 2 main reasons are the physical one, the one I told you, and the mathematical one is that this object, if you define in this manner, does not have well-defined Lorentz invariant property, while here it has, and is a 4 vector as dxi. And in fact, we have seen last time that the X and T transformation are very similar to the P and E transformation. And let me rewrite all of them. Okay. Let me use the convention I use in this. Last lecture we saw that with this definition, where this is proper time, then the P and the E also makes a 4-vector, and their transformation are the following one. Let's suppose we are just in one space dimension. Px is equal Px minus E v c square, and E minus Px v 1 minus v square c square. Both of them, we will return on this issue, both of them now are 4 vectors, in the sense that it's possible to see, dividing properly by C, that this quantity transforms in a manner that is very similar to this, and so on and so forth. So is that clear a little bit? But you know, we will repeat and repeat and repeat things till, so we will not move away from the same topic, more or less, in these 5 lectures, okay? They will all be very strict, so you will slowly digest, okay? Now, what I wanted to do, yes, I wanted to do the homework. Now, if you remember, you see, for example, on page... why this proper time is very important. This proper time is defined in this manner. Delta t c is equal square root of c square delta t square minus delta x square. Now, why this is very important? First, this is a sort, as I already mentioned in the first lecture, of pseudo-length. You know, analog, if you have the rotation, in the rotation the length is this, and there is, and this is invariant under rotation. This object, I call proper time this delta t because this is the dimension. This quantity, despite the fact it has a minus, it is invariant under the analog of the rotation, that is the Lorentz transformation. So this quantity is invariant. But not only this quantity is invariant, this quantity is invariant under Lorentz transformation, so it is the same, so I don't have to change in the denominator of the definition of momentum. But it has another important feature, that means it has a physical meaning, and the physical meaning, I don't remember if I wrote, which actually I wrote. Yeah. It has the following physical meaning. If you take delta t prime from there, is equal delta t minus v c square delta x 1 minus v square c square. Let's suppose we are in the frame with the running with the particle. Then there is no displacement. If we are with the particle moving, there is no displacement. So this is 0, and delta t prime is equal delta t 1 minus v square c square. So it has also the meaning, this delta t, sorry, you take it from here. Take it from here. If delta x is 0, you see that is the interval of time in the frame that does not move. Okay, so this is proper time. Now, there are many manners in which we will indicate these. some books, just it's important that, I mean, I took 3 different books because it's important. This quantity sometimes is also called S or ds, okay, for proper time. If you reverse these, you know, if this is invariant, also the opposite one is invariant. And then you have delta x minus, and then it is called proper length. Okay, just, now let's go to lecture 2. In lecture 2, we did not actually finish all the chapter, all the lecture. What I sent to you is a little bit more. There is, do you have a question? Please.
I think there was a problem for contraction of
What? Yeah. Which page and which lecture? The first lecture, tell me. Page 7 and 8, okay. I don't understand. Can you speak? Yes. Address with the particle.
Yes, with the particle, yeah. But when we define it's like it's not in the frame, it is the frame for the particle. Because the frame is...
Yeah, in fact, that means, let's say, no, okay. Here in the contraction of length, I only show that length in a moving frame look contracted with respect to the rest frame. Where do they talk about invariant length? Here I don't talk about invariant length. In this page 7 and 8, I only talk about contraction of length. Here, if you read page 7 and 8, I talk only about contraction of length. So L is in the L0 is in the rest frame with the system, and L is in the moving frame. Okay, and then I prove at the end of page 8 that there is a contraction that.
Usually, the moving frame is marked with prime. But
yeah, here is with prime. Look. Look at formula 8.2. L, I define L as x2 prime t prime minus x1 prime t prime. So I should have called L prime that. Oh, but that is a question of not.
But I think L0 should be the length with x prime minus x prime.
No, because I define myself L0 as that. You know, the point is this. Tell me if in the various steps that I did, there is a mistake. If there is a mistake, then I agree with you, a mistake in the calculation.
No, not the mistake, but maybe the notation.
Oh, the notation I don't care. I mean, that means there are, I told you, there are various notation in various books. What is important is that what I define. So I define L0 as x2 minus x1, and I define L as x2 prime minus x1 prime. But you know, it is important, these kind of things. That means I be careful to the notation, not having a standard notation in mind, but what I defined. Okay, this is a very important. You did a good exercise in this manner, you understand? So do yourself also this kind of thing. Okay. Okay, so let's go to lecture 2. I said lecture 2 we did not finish. There is, from page 7 on, there is something called group structure. For the moment, I put on that lecture, but we will skip because we will do lecture 5, I think, with a lot of group structure, Lorentz and so on. And so we will skip for the moment the section that is one page of lecture 2 where there is group structure. You can skip that. I mean, if you read it, does not hurt. But now let's do the homework that is on page 7 of lecture 2. So it does not mean that I will not require that you submit that homework, but I will help you. And I will help you just because due to the notation, it might be that you get confused. But I will help you. I will not submit. I will only write on the blackboard. I will not submit the detailed calculation. Okay. There, what did I do? I said, let's take rotation. Okay, along Z. And we know that rotation along X, the X and Y change in this manner. Cos theta plus Y sin theta minus X sin theta plus Y cos theta. Okay. And I told you Lorentz transformation have the same feature as rotation. They keep invariant a length that I call the pseudo-length because they are not plus, 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 but it's plus 1, minus 1, minus 1, minus 1 if we are in 4 dimensions. The homework was prove that for a Lorentz transformation in xt, the transformation can be written in this manner, and I use a very fancy notation that is this, dt cosine hyperbolics of xi minus dx sine hyperbolics of c, and dx tilde is equal to dx cosine hyperbolics of xi minus d tau sine hyperbolics of xi. And I said, look, dx tilde over d tau tilde is equal to v over c, and cosine hyperbolic of xi is equal to 1 minus v square c square. Now, why this is a nice notation? It's a nice notation, and of the 3 books I suggested, it's very much underlined in the book of Schwartz, if you want to give more detail. And that book of Schwartz, the chapter that we use are on PDF in the library. You can go to the loan desk and said, I need the PDF of the book of Schwartz. They give to you, okay? They download for you the PDF and give to you. I got this agreement with them. Now you see that it looks very similar. Here there is xy, there is xt. So this is rotation, this is Lorentz. And you see, instead of sine and cosine, you have cosine hyperbolic, sine hyperbolic, and so on and so forth. Now, the homework was prove that this is the Lorentz transformation. Okay? So how we do that? Well, let's remember, so I want to prove that this, that looks very similar to a rotation, but sine and cosine have been replaced by these cosine hyperbolic and sine hyperbolic, is the usual standard Lorentz transformation. Well, the usual standard Lorentz transformation for interval of time, here I call differential, but you can call delta t or delta x. So delta t prime we know was delta t minus v c square delta x, 1 minus v square c square, and delta x prime is equal delta x minus v delta t, 1 minus v square c square. Remember, this is the Lorentz rotation. The homework was prove that this can be written in this once you use this formula. Okay, so here, just to make you think, I use this strange notation, and you might think that this is the proper time. No, this is the normal time. But actually, if you look from here, it is something more than normal time. Let's define, I mean, basically here the manner to do it is to find out what was tau prime. Let's define tau prime in the following manner, Tc. and tau, sorry, T prime C, and tau as TC. This has nothing to do, sorry, T tilde. This has nothing to do with proper time. It's just a definition, okay? So here the homework was that maybe you thought this is proper time and then you run into trouble. No, this is the Lorentz transformation. So this cannot be proper time because proper time does not transform. Okay, so from that thing you can say, oh, even if you call in that manner, it is not proper time because here it transformed. So it is something else. And in fact, it is easy to see that this tau tilde and tau is basically T prime C and TC. Let's in fact multiply this quantity by C. We get delta prime C equal delta T C minus VC delta X 1 minus V square C square. Then we get delta X prime equal delta X minus VC delta T delta tau okay, so I have multiplied the first by C, both sides, left and right hand side, and I get C here, and then VC square multiplied by C, it becomes V over C and delta X. Then I want to use tau also here, but we know that tau is that T and tau are related by this relation. So delta X minus VC delta tau divided by this. So this is the relation. And of course here I can now put this object from this definition. This object is delta tau tilde and this object is delta tau. Okay, so this thing is delta tau tilde is equal to delta tau minus VC delta X 1 minus V square C square, and delta X prime is equal delta X minus VC delta tau 1 minus V square C square. So this is the relation in a form that is sort of similar to this one. Okay, so this, let me rewrite now this. We will put it here and cancel all the rest. So what I've done, take the normal Lorentz relation, multiply by C, and I get this. Then, as I define this quantity in this manner, tau tilde is T prime times C, and tau is tau T times C, I replace here with delta T, delta tau tilde, and here with delta T, I get this relation. So let's now cancel all the rest. And now we have a relation that looks a little bit more similar to this, but we don't know if it is the same, okay? Can I cancel? Okay. So delta tau tilde is equal to delta tau minus VC delta X 1 minus V square C square, and delta X prime is equal delta X minus VC delta tau 1 minus V square C square. I said, can I cancel? What did you say? But that one I rewrote here. This one I rewrote there. Okay? Okay. Now let's manipulate this one and see if we can get into this form. Let's first look at the definition. This strange psi is defined in such a manner that cosine hyperbolic of psi is this quantity. So, okay. So you see, this one I can write delta tau times 1 over V square C square minus VC delta X 1 minus v square c square, the first relation. But it means delta tau cosine hyperbolics of psi, because cosine hyperbolics of psi is defined in this manner. So psi is a quantity is related to this. Then for the moment, let's see, we have Vc delta x 1 minus v square c square. Now I will show to you that this quantity is cosine hyperbolic. Why? Okay, you remember there is that famous relation cos square x plus sine square x is equal 1, but there is an analog one for the hyperbolic quantity that cosine square minus sine hyperbolic square is equal 1. Okay, then remember the analog of the trigonometric one is this second one. I imagine that all of you know this. So let's insert here the expression cosine hyperbolic square is 1 minus v square c square minus sine hyperbolic psi is equal 1. So from here we derive what is a sine hyperbolic square, sine hyperbolic square, you bring on the other side and you get the plus. Bring the 1 on this side and you get that is equal to v square c square 1 minus v square c square. Okay, so the sine hyperbolic psi, if I choose the plus sign, is this quantity. And then here, sorry, here is right. There is no square root. Okay. So you understood. I started from the analog of this, that is this. I inserted the expression of cosine hyperbolic, that is this. Here I put the square, of course, and then I get this relation. From this relation, I get that sine hyperbolic square is this. And then having done that, then I can rewrite this as equal delta tau cosine hyperbolic psi minus, this is sine hyperbolic sine delta x. So the first relation is proved. Instead of using d tau and dx, I use delta, but it doesn't matter. Okay? So I have proved the first relation. Please. This is just a convention, okay? And if you say, well, I take the minus, it's like reversing the velocity, okay? So I cannot give you any better explanation than that one. But, okay, so the first one. We have to derive the second one. Let's see. It is not more difficult than that. Let me... So the first one we have derived, so we have proved. You have to be quick. Otherwise, you know, it's like if I had done the homework, you redo it at home. And in that manner, you get trained. You do some exercise. So otherwise, your problem is just a problem of copying it. And that is not a good... Okay, so this one we have proved. Now we have to prove the second one. Let's remember this relation. Let's keep it down here. That sine hyperbolic is equal v over c, 1 minus v square over c square. You know, there was a teacher, I don't remember, a famous one, who used to do the following thing. Write, and as soon as he writes, with two hands. One he writes, the other he cancels. I did on purpose, so that means you have to memorize or understand the step, and so it takes me even too long to cancel it. So. Now let's see this one. This one is delta x times 1 minus v square c square minus delta tau vc 1 minus v square c square. This was the cosine hyperbolic, so we get delta x cosine hyperbolic of psi minus delta tau, and here we have the sine hyperbolic. Okay, so done. That means we have proved what the homework wanted, which was the difficulty here. And I realized yesterday that that you do the wrong mistake of considering this the proper time. But you know, even if I use this strange notation, you should realize it's not the proper time. Now let's go a little bit further into this problem, because now I want really to bring this into a form that resembles very much this, without sine hyperbolic and cosine hyperbolic. Let me, so now I want to bring this into a form with sine and cosine. This is not part of the homework, of course, but it was. Well, there are these transformation formula that the cosine hyperbolic of Ix is equal to cosine of x, and the sine hyperbolic of Ix is equal I sine of x. Are you familiar with this? It's very simple. You know, you take the definition of cosine hyperbolic and sine hyperbolic, that is exponential, normal exponential. You take the definition of this, that is exponential, but with the I, you compare and you get this. Do this as a simple exercise, okay? Then from here, you derive, it's easy to see, that cosine hyperbolic of x is equal to cosine of minus Ix, and this is cosine of Ix, and sine hyperbolic of x is equal I sine minus Ix, and this is equal, what did I do here? No, is this manner. Let's see. Let's take this. Let's call this x. Then sine of x. X is minus I, so it's minus I. Let's see if I did it right. Sorry. Huh? There is no I in the front here. There is. Okay, let's just do it. So if I call this x, then this object is minus Ix, and I am right, but there is an I. There is an I. So this is minus I sine Ix. Then what I had in mind does not come out right. Check it at home, okay? Here there is a minus I. I corrected and I put a plus, but okay, minus I. Then if it is a minus, it's plus. Okay, I don't have the booklet with the formula, so please go and check it. For me, what is important is just this, because now, look what we get. We get delta tau. Instead of cosine, we put cosine ix minus delta x, and here I put an plus I sine ix, and then I add for this one is equal delta x cosine ix, and then I have minus, so I get plus I, there is something wrong. There is something wrong, but okay, it's a problem of sign, I don't care very much. I sin ix. So check at home these things. I just wanted to show you which structure come out with that cosine hyperbolic and sine hyperbolic. This is the things. And let's now compare with x and t. Sorry, here of course is xi, and xi. Now I want to compare this one with that one, so there is a minus that is wrong. Check the sign, at least you do this part of the homework. At the end, this one should be delta x prime is equal minus delta x sine ixi plus delta y cosine ixi, and delta tau prime is equal minus delta x sine ixi plus cancel, sorry. Okay, let's compare this with this, but there is a problem of some sign. Delta t prime is equal delta t cosine t. Here there should be here there should be a delta and no I, and delta x, and here there should be also minus delta t. So check in the transformation from cosine hyperbolic to sine hyperbolic, and the final formula should be this. And you see that these resemble very much the rotation things, because this one you can write in this manner, minus delta x. Okay, this one you can write delta x prime is equal delta x cosine ixi minus delta t sine ixi, and delta tau tilde is equal minus delta x sine ixi plus delta t cosine ixi. Okay, so I've taken these two. These are the ones to be checked, okay, because I did a mistake in the transformation of the cosine hyperbolic and sine hyperbolic. This should be the one that is checked, and then this one is equal to this. And look how much it resembles this formula. If you take x to be x, and if you take y to be t, you see this is a Lorentz transformation, but it looks very much like that. It's just that the argument of the sine and cosine are now imaginary, but the form is the same, delta x minus delta t, and vice versa. Okay, just so which is the modulo the factor of I that I want you to fix, and that this formula that we have proved is a Lorentz transformation going into imaginary quantity becomes this. So the Lorentz transformation is something like a rotation, but in which the argument is an imaginary argument. We will go into more detail into that. Yes, please.
Suggest if we multiply as it were like plus plus, but if we multiply by I, everything would be I delta x, because zero are
maybe. Okay, check at home these things, okay? I don't want to spend more time on this because it's not... what I want to do now, as we are in between, roughly halfway into the review of special relativity, you see this review of special relativity, I could have skipped in the sense that you are supposed at this stage to know special relativity. I imagine that many of you have already done. So this part I have to go sort of quick because you are supposed to know general special relativity. So now what we will do is we will do some problem. You will have further problem, one or two, done by an instructor named Madi. I only remember his first name, Madi. Okay. So let's do some problem. And these I will send to you today after class. Please.
Can I ask something?
Yes.
Okay. The second postulate of special relativity is the invariance of the speed of light in
Right.
right? Why the speed of light in an inertial frame of reference?
What is the question?
The speed of light in an inertial frame of reference.
In an inertial frame of reference.
Non-inertial.
Non-inertial, then you have to go, you see, we treat only how to go from one inertial to a non-inertial. General relativity developed 12 years after special relativity answered that question. Okay, that means all things change if you go from an inertial to a non-inertial things. And well, what happened is, well, I don't want to enter here now, but anyhow, that is what is being answered by general relativity. That was the next question that Einstein asked himself. Does this, you know, basically space and time change in a different manner than in the Lorentz case? And as far as I'm not an expert of general relativity, but I think the velocity of light remains the same, even if you go in a non-inertial, but don't take my words for granted because I'm not an expert of general relativity. But to say how things transforming going from inertial to non-inertial frame, that is being answered by general relativity. And it tells you that the metric, you know, that metric that we have already introduced, 1 minus 1 minus 1, change. And it becomes not anymore a constant all over space-time, but it depends from the point in space-time. So instead of having 1 minus 1 minus 1, you have functions of x, and it might not even be diagonal. That is the only things I know. I'm not an expert of general relativity. If I remember well, the velocity of light should not change, but don't take for granted that. Okay, let's do some simple problem now. And the problem are all about proper time and so on. Now, so the first problem is the proper mean lifetime of a particle. For example, let's take pi plus mesons. So the proper mean lifetime, that means we measure its mean life, see how long it takes on the average to decay, and but proper in the sense that this is the proper time, so that means we are moving with the particle. We are not looking at the particle while it decays, we are moving with the particle. And it's 2.5 times 10 to the minus 8 seconds. Now they say that is the proper, and is really the quantity that characterizes the particle. That means if you move with the particle, okay, at the same speed, you will see that on the average, that is a mean life, they decay after this time. Now, if instead we have a burst of particle coming down from the atmosphere, and their V over C, that is usually called beta, and this beta, you know, goes from 0 to 1 at most, because is 0.73. Now they want to know, with a beta of 0.73, which is the mean life, not the proper mean life, the mean life. That means, you know, if the particles are moving in this manner, is something like you can consider that you are looking at them moving in a reference frame that goes in the opposite, with the opposite velocity. So that means, you understand, they are coming down at this speed. If you sit with them, their mean life is always this. But now we are not sitting with them. We are looking at them coming down with this thing. So we could also imagine that we are in a frame that moves with the opposite velocity, and we want to know the mean life. So mean life in this frame. Okay, so we have a frame moving. We can consider them, instead of them coming out, that we are moving up and they are at rest. And so we want to know the mean life in this frame. Now, we know that there is time dilation, and that the formula is delta t prime is equal to delta t 1 minus beta square. That was the formula that tells me in the moving frame, and somehow I am in the moving frame, it means I am not sitting with the particle at rest, is equal to the delta t, that is the time on the particle at rest, divided by this factor. So you insert, you have 2.5 times 10 to the minus 8. This is this number, divided by 1 over 0.73 square. You do this calculation, and you get 3.66 times 10 to the minus 8 centimeter. So a burst of particle seems to have a mean life longer. This delta t, this one, is bigger, longer than this one, okay? Now, centimeters. Sorry, second. I'm sleeping. Okay, now the second question they want to know is the distance traveled by the pi plus minus before decaying, because, you know, we don't measure time. We measure when they are produced, the pi plus come from some other decay, and we measure where they decay. So we measure distances. And the distance will be beta times c, because beta times c gives me the velocity, times the interval of time, delta t prime, because, you know, they are moving, so I am in this reference frame. I'm not. If I ask you, which is the distance if you run with the particle? 0. If you are across like a horse riding this particle, you know, you get 0 distance, but we are not, so we have to use the time in the correct frame, and this is the time in the correct frame. So you get we put in 0.73, then the velocity of light is 3 times 10 to the 10, then we get 3.66, 10 to the minus 8, and what we get is 802 centimeter, just roughly, huh? Just do with your calculator. Now they ask which, see, so this is the second question. Distance traveled without relativistic effect. Then without relativistic effect, that means there is no time dilation. You have to use this time, okay? And then you get 0.73 times 3 to the 10 to the 10. This is the velocity of light. This is c. Times 2.5, 10 to the minus 8. And this is 548 centimeters. So you see, the distance covered, looking at them from the Earth, is bigger. So this time dilation is a physical effect. Look, there is almost 250 centimeters. That means 2.5 meters more, considering this effect. So it's a measurable effect, right? If you take account of the relativistic thing. Well, this I will send to you. So, can I cancel? You will get everything in half an hour, in an hour, so don't worry. Second problem. Now we take another particle that decay, that is the mu meson. The pi plus meson decays into mu plus other things, while the mu meson, they decay, the mu meson, I forgot in what they decay, but okay. Now, again, proper, remember there is always proper mean life time is 2.0 minus 6 seconds. Now let's suppose that a large burst of this particle is produced at some height in the atmosphere and the velocity is 0.99 c. Okay. Let's suppose that basically the collision in the atmosphere is negligible, and we know the only 1% survived on decay and reached the Earth. 1% reached the Earth. So now they want to know if 1% you count. Somebody up there said, I have thought 2 million particles. And you look at that down on the Earth and you get only 1% of that. They want to know how much is the height. Well, first of all, we should remember the law of decaying. If this is the number of particles at times t, and this is the number of particles at time 0, the usual things is this, where the usual law of decaying of unstable particle is this famous exponential, where this is the proper mean life time. So time t, if n0 is the number of particles at time 0, at times t the number of particles is given by this formula, where t is the time and tau is the proper mean life. So let's now n tau over n, sorry. Now we know that this n is the number of particles surviving is 0, 0, 1, and 0. Because 1% survive. If this is the things, then we put in 0, 0, 1, and 0 is equal to n0 exponential minus t over tau. And then we get e minus t, but tau we know. Tau is given is 2 divided 2 times 10 to the minus 6 is equal to 0.01. Okay? So what I do, I cancel this, t I take, and tau I put 2 times 10 to the minus 6. You solve for this equation, okay? Just you have to take some log, and what you get is t is equal 6, t is equal 9.22 times 10 to the minus 6 seconds. But these, you remember that here we use the proper lifetime. So this is the time in the proper frame, that means riding with the mu particle. So we have to transform this. This is the mean, this is the proper time. We have to look, because they want to know the distance, and we are looking from the Earth, we have to transform to the time on the Earth, not riding the particle, but seeing the particle that we ride. And then, of course, it will be time dilation. And what do? You do take the time, 10 to the minus 6, this one, the proper time, and divide by the contraction factor, 0.99 square. Okay? And the result is 6.54 times 10 to the minus 5 seconds. So this is the time it takes to get to the Earth if on the Earth we get only 1%. Is it clear, the logic? This is the general time. Here, this is the proper mean lifetime, and this is the time in the mu reference frame. That means riding with the mu. NT is 100% of N0, so I put this number in, I get this, and from this I get the time it takes, that is this proper time. The time on Earth will be dilated with respect to this, so you use the usual dilation formula. Here you put this, and here you put 1 minus V over C squared, and you get this number. This is the time it takes. Now the distance, well, the distance covered is 0.99 of the velocity of light, okay, times the time. So this is the velocity times the time, 6.54 times 10 to the minus 5. I think I did a mistake. 0.99, but I have to multiply by C. So I have to multiply by C. In the notes, then there is a mistake. I will not correct it. Then you get 318, something like 19.5 times 10 to the 5 centimeter. And this is in the frame of the Earth. If you measure, okay, so I got a different number here because I did not multiply. Most probably I multiply, but I forgot to insert it. 0.99, and then I did not put the velocity. I took the velocity, but I did not put 10 to the 10. No, I put, but without, you have a pen? Can I borrow a pen? Thank you. Right. I get a number that most probably is not correct. And the next question is, this is the distance seen from Earth. The distance covered seen from the mu, then it is contracted. That means the d seen from the muon is this distance contracted. And then it means you take this distance and multiply by 1 over v squared c squared. Insert the number and you get the things. Okay. Let's do a third problem. You see, the number of problems I'm doing is much more than the number of homework you have to submit, plus you will have some other things. So problem 3. We observe a galaxy receding in a particular, so galaxy A and galaxy B. We have, okay, so we observe a galaxy receding in a particular direction at 0.3 the velocity of light, and another one receding in the opposite direction with the same speed, 0.3c. So A and B are two galaxies. They are receding with the opposite direction. It says, what speed of recession would an observer in one of these galaxies measure for the other galaxy? That means this is what we see staying in a reference frame with respect to which both galaxies are moving at the same speed but in opposite direction. Now, if we sit in frame B, which is the velocity at which we will see the galaxy A receding, this we have to use the composition of velocity formula. If you remember the composition of velocity formula, it was the following: Vx minus V, 1 minus Vx V over c squared, where Vx is the velocity in the Vx was the velocity in the old frame, and Vx prime is the velocity in the new frame. V is the velocity of the frame with which we move. Now, let's take galaxy A, and for galaxy A, its velocity is minus Vx, because it's going into this direction. Now, the velocity v square is the velocity v, capital V, as we sit on galaxy B and we want to see at which speed galaxy A move. V is nothing else than Vx of B. Okay, so this is the speed of the frame, and now if we sit on this frame, the one of galaxy B, this V, that is the velocity of the frame, is Vx of B, but Vx of B is Vx. Okay, now we have all the number to insert here, so we want to see the velocity x prime of galaxy A, and we put in Vx of A minus V, 1 minus Vx of A, V over c squared. So we want to see the velocity of galaxy A in the new frame, and we have only to change and put here Vx. So we put in Vx, so we have Vxa is minus Vx, Vx, minus Vx. Yes?
It's not V prime, X prime?
V prime?
Seems like V prime is...
Oh, yes, 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 of course. If you want, we can put a notation guy. I'll call you from now on, okay?
We can express X prime.
Right. I meant that in putting, but it's a new velocity, right? It's a new velocity, so I put the prime there. I know that I'm changing frame, so the correct notation should be this, okay? I agree. Sorry, don't feel offended that I give nickname, huh? Don't, okay. It's good that he point out these things, because in that manner I stop and explain, you see. So do it, please keep doing. Don't worry if I keep you notation guy, okay? Okay, now Vxa is minus Vx, and V is Vx, so we have minus Vx, divided minus Vx, so here we get a plus, and then V, and this Vx, and then divided by c squared. Now Vx, that is this is Vx, and this is minus Vx. We know is 0.3, so we get minus 0.3 c plus 0.3 c, 1 plus 0.3 square c square times c square over c square. Okay, and do this calculation. You understand what I did? This The difficulties on this problem is in finding out which is the velocity of what, okay? So here, this is the velocity of the galaxy A in the frame we were before. The velocity of galaxy A is minus Vx, because it's going into that direction. And then we have the velocity of the frame, but which is the velocity of the frame? We are on the frame B in changing frame, because we want the velocity of A in the new frame. The new frame is the one that is going with B. So basically, is the frame velocity is Vxb, and Vxb is Vx, because this is the positive direction. So you insert all that. Here you get a minus, because Vx is minus, Vxa is minus Vx, so you get a plus. V, you get this number, and so on. Now, if you do this calculation, what you get is 0.55c. And you see that this is less than if I had added naively and said, oh, come on, in a non-relativistic way, add in a non-relativistic way, then the velocity of A seen from the frame B would be 0.6c, right, in a non-relativistic frame. You just add the two velocity. Instead, in a relativistic frame is less. And you know, there are galaxies that move at this speed. Any question? Then I cancel, okay?
So it's wrong to add two velocities.
Right. To add two velocity just naively like you do in relativistic things is wrong. You have to use the additional velocity of relativity that has this extra denominator. Okay? And remember, you know, all this is related to the fact that the velocity of light does not change, is the same. Okay, now, the proper length of a proper length this time, problem 4. The proper length of a spaceship is 100 meters. That means if I am in the spaceship with another astronaut, we are traveling in the spaceship, and they said, how long is the spaceship? And inside the spaceship, while moving with the spaceship, we measure, so inside the spaceship, going proper, it means you are riding with that thing. The proper length of the spaceship is 100 meters. Now, another astronaut is outside, and the question is, John is addressed outside the spaceship and measure a time interval of 2 microseconds for the spaceship to pass him. So this guy is not inside the spaceship, is outside, and he realized that for the spaceship to pass him, it takes this time, which is the relative velocity of the spaceship with respect to John. Okay, so this is the picture, and here is the spaceship. This is the spaceship, the two other men who are inside. They measure, staying inside. This spaceship is going at some speed. He is outside at rest. These one are inside, they measure, and the proper length is 100 meters. They move at some speed. He has not, he cannot run after he goes very fast, so he measured the time, and with his watch, he measured the time, and he get that it takes 2 minus 6 seconds to pass him. Okay. Now, for sure, he will see a contracted length with respect to the proper length. So the length he sees is L0 times 1 minus v squared c squared. Because, you know, you can imagine that if you consider this at rest, it's in a moving frame, if you consider this at rest. So in a moving frame, you see a contracted length. E is at rest from outside, but with respect to them is in a moving frame. So E sees a contracted length. That means this is the length E sees. So let's put here 100 meters. Let's put in centimeter. So this is the length, the proper length. Then we get 1 minus v squared that we don't know, divided by 3 to the 10 to the 10 square. And this is the length. Now, this is the length he would measure, but he does not measure a length, he measures time. So the time he measures, delta t, will be L over the velocity at which the spaceshift moves. Okay, it is the same as this, so let's put 10 to the 4th, 1 minus v squared, 9, 10 to the 20, is this number, divided by v. So v is our unknown quantity. This delta t we know. Delta t is 2 times 10 to the minus 6 seconds is equal to this expression, 10 to the 4th, 1 minus v squared, 9, 10 to the 20 over v. And this is an equation for v. You solve this equation, you see, just square this, do all the steps. And what you get is that the v, from here you derive that v is 1/2 c. So that spaceship is going at this speed. You know, it's always very important to find out the right reference frame, okay? It's very easy to make mistake. They have measured this distance, and for them, E is in a moving frame. They are at rest, because they don't see any movement, they are inside the things. So for them, E is moving. So if he is moving, he will measure a contracted length with respect to this one. Okay? It's very easy here to do mistakes in this kind of problem. Remember, especially for the homework, the final exam will be a simple problem like that, you know. Maybe I will just try to get you confused, giving strange notation and so on and so forth. And then if I call tau and you see that it changed like before, you say, okay, this cannot be the proper time. You understand that kind of a small trick that I will use. Can I cancel? Okay. Problem 5. This problem 5 is on the last part of last lecture that was on the energy concepts. Last time we talked about the total energy of a system. So the problem is problem 5. An electron has a beta that is V over C of 0.99. This is a number, you know, because it's a ratio of two velocity. They want to know the kinetic energy. Now, we know the expression of the total energy, that strange expression we got last time, mc squared divided 1 minus beta squared. That was the total energy. And if you remember, if you expand in case V is small, is the kinetic energy plus the mass energy and so on and so forth. Now, if we want the kinetic energy, we don't expand, but we take the total energy and subtract the mass energy. The mass energy was mc squared. Here in this problem, I think it was given a few years ago as an exam, Many people did an expansion in beta, but you cannot do an expansion in beta, okay? And it's true, well, that is less than 1, but it's not very, very small, so. Now, you cannot do this expansion because if you do the expansion, you would get the 1mv square plus mc square plus extra term, okay? I did not ask the non-relativistic kinetic energy. I asked the kinetic energy, period. That means relativistic, so that means you have to do this plus all the other term. You understand? But then the other term, you would have to continue the expansion. It's not that you cannot do, you would have to continue the expansion. But then it's much better to define kinetic energy. That means the energy due to the motion. All the energy that is this, the non-relativistic part, plus this. You only subtract the energy that is not due to motion, that is due to the mass. Okay? So that is what you do. Then let's insert, okay, this is mc square. Then you get this object, 1 over 1 minus 0.99 square minus 1. Then you get mc square. You calculate this number with your calculator and you get 6.7. Then the mass of the electron is 0.51 MeV, and then you get 3.10 MeV. Okay, so this is the kinetic energy, and you see at this speed, the kinetic energy is 6 times more than the mass of the electron. And this is a very important thing. Any question? Remember this expression of the total energy that we derived last time, and we will go into more detail on Friday about the concept of energy and so on. They are all very simple and very quick, this problem. Now, where there are a lot of problems of those 3 books, on the Berkeley course in physics, of the 3 books I suggested, there are a lot of problems that you can do, and these I took from there. On that book, Mechanics, Berkeley, of the 3 books I suggested, there are a lot of problems there with solution. Problem 6. Now, you have a nucleus of iron, F57, and this nucleus of ions emits a gamma, a photon. Okay, so that means first is at rest, and then you have this situation. And then, of course, they will move in opposite direction. So it said, what is the recoil momentum in the laboratory of a nucleus of iron due to the emission of a 14 keV gamma ray? 14 keV gamma ray. Is velocity, so it will recoil, it will emit, and then for conservation of momentum it will recoil. And which is the velocity that he has? Is it relativistic or not? Okay. Well, first let's look. Everybody start looking at this, but it's wrong. Let's look at the photon. The mass-energy relation for the photon is the following. You know, here there should be m squared C4, but m is 0. So for the gamma, this is the relation. That means the momentum of the gamma is E over C. Plus minus, but we don't care about the direction at this moment. I have derived from this relation. Now let's put in the 14 energy. We know is 14 keV, so 1.14 keV. We have to turn into erg, and the conversion factor is -9 erg. Okay, so kilo electron volt, the conversion factor is this, divided by C, 3 to the 10 to the 10, and you get 7.5 times 10 to the minus 19 gram per centimeter divided by second. Now, of course, this is the recoil momentum, but you want the recoil velocity because you want to know if it is relativistic or not. Then we need the mass of the iron 57. So you look on the table, or if I give the problem like that, I expect that you ask me, which is the mass? If you don't ask me, it means you are not able to do the problem. So I give you the mass, and the mass is 9.7 times 10 to the minus 24 gram. I have the recoil momentum, so the velocity in the sense of the proper velocity. That means this is dx d tau, okay, this times m, this velocity I want. Then the velocity is 7.5, I take from there, 10 to the minus 19, that is the momentum. Okay, so this is pi gamma over m. This is the velocity, divided 90, this is 97, times 10 to the minus 4, and I get 7.7 to the third centimeter per second. And this is not relativistic velocity. Relativistic velocity are of the order of 10 to the 10. Okay, yes? Yes, it's addressed initially. Of course, it is excited somehow. Then it emits a gamma ray, a photon, and then it moves in the other direction to conservation of momentum. And they want to know at which velocity it's moving. It's moving at this velocity, is not relativistic. Last problem. Problem 7. Okay, here again on energy, but now they want to know the mass equivalent of some energy. Means we know so he said, what is the mass equivalent of the energy emitted by an antenna radiating 1000 watts for a period of 24 hours? Okay, now remember 1 watts is 10 to the 7 erg per second. So 1000 watts is 10 to the 10 erg per second. 1 day is 24 hour times 60 minutes time 60 minutes, 60 seconds, 24 hours. In an hour there is 60 minutes. In each minute there are 60 seconds, so I did a mistake here. I want to put in power of 10, am I right? 24 hours, 60 minutes each hour, 60 seconds in each thing, so we get 700. Let me, in power of 10? 8.6 times 10 to the 4. Okay. Now, they want to know the mass equivalent. The mass equivalent, it means you use as relation E equal mc squared, like if this energy or photon emitted or radiation emitted were addressed, okay? That is the mass equivalent. So when they ask you the mass equivalent, you use this relation. So basically what you do, So this is 1 day, so the total energy emitted is 10 to the 10 erg per second times 8.6 times 10 to the 4th. And so you get 8.6 10 to the 14 erg. Now the mass equivalent, you take E divided by C square, so 8.6 times 10 to the 14 erg, divided by the velocity, that is now square, 10 to the 20. Okay. And this is centimeter per second. This is the number that one should get, but then it has to go into gram. Is this the correct things to get things into gram? Question. No. Okay, so get the convection factor, and it should be of the order of 10 to the minus 3 gram square. And then you get in gram, okay, and is of this order. So the mass is a milligram roughly, but do the calculation correctly. Okay, so Friday we will start doing again lecture again on dynamics, and we will do the dynamics of two objects scattering going into two other objects, and introduce some quantity that will be very useful. Have you done scattering in quantum mechanics somewhere? Not? Okay. We will introduce what are called the Mandelstam variable and center of mass system, threshold energy, and so on, a little bit of the physics that is done in accelerator. So that lecture will be called Relativistic Dynamics 2. And then next week, I think we will do the last lecture on special relativity. That will be on group theory and Lorentz group and representation of groups and so on. So